Hi everyone, welcome back to Chem Help ASAP. In this video, we are going to talk about Le Chatelier's principle. Let's get started. Le Chatelier's principle states, any stress applied to a system at equilibrium will cause the equilibrium to shift in a direction that reduces the stress, which sounds very general, I know. And for the principle here, it needs to be in general, but let's take a look at some specific cases. So first, let's talk about when we change the amount or we change concentrations. I'm going to start with just a very generic equilibrium equation right here. A plus B going to C plus D. One way we can change the amount is we can increase the amount or increase the concentration. Okay, so if we're going to increase amounts, what happens to equilibrium? Well, our general rule is that increasing the concentration will shift the equilibrium away from the increase. Now let's get really specific. So let's increase the concentration of A. If we're going to shift away from the increase, we're going to shift the equilibrium to the right or towards the product. Okay, now let's look at what happens if we increase a product. So let's increase the concentration of D. Again, we're going to shift the equilibrium away from the increase, so that will shift the equilibrium to the left or towards the reactants. So if you are increasing an amount of a reactant or a product, your equilibrium is going to shift away from that increase. Another way we can change the amount is we can decrease the amount or decrease the concentration. So our general rule of thumb is that decreasing the concentration is going to shift the equilibrium towards the decrease. So this is the opposite of increasing amounts, which makes sense. So let's look at some specific examples. So what happens if we decrease the concentration of B? Well, we're going to shift towards the decrease. So we're going to shift the equilibrium to the left or towards the reactants. Okay, so now let's decrease the concentration of C of our product. Again, we're going to shift the equilibrium towards the decrease. So we are going to shift the equilibrium to the right or towards products. So just to reiterate, if you're increasing amounts, you're going to shift away from the increase. A decrease in amount is going to shift the equilibrium towards the decrease. So changing the amounts is one way we can apply stress to an equilibrium and cause a shift in that equilibrium. But there are other ways that we can cause stress to a system at equilibrium. We can change the pressure of the system. So here we went with a specific reaction, of course, the formation of ammonia. Let's take a look at changing pressure. So one way we can change pressure is we can increase the volume. Of course, this decreases pressure. So we're going to take a reaction vessel and we're going to make it much larger. So an increase in volume is going to shift the equilibrium towards the side with the most moles. Well, what does it mean to be the side with the most moles? This is why it's helpful to have a specific example here and not a generic equation. We are simply going to add the stoichiometric coefficients on each side. So the moles on the left-hand side or the reactant side of the equation are 3 plus 1, and that equals 4. Again, the 3 is from here, and the 1 is in front of the nitrogen. So we have 4 moles on our reactant side. On the product side, or the right, we only have 1 product. We only have 2 moles, again, because there is a 2 right here. So we have 2 moles on our product side. I like to think of this as when you're increasing volume, the reaction wants to make itself as big as possible. So it's going to shift to the side with the most moles, which in this case is going to be a shift to the left towards the reactants. Now let's go opposite. Instead of increasing volume, let's decrease volume. Now that is going to increase the pressure. So we're going to take a container and we're going to shrink it down. So when we decrease volume, we're going to shift the equilibrium towards the side with the fewest moles. Still using our example here, we've actually already calculated our number of moles. Again, the moles on the left are going to be 4. The moles on the right are 2 because we haven't switched chemical equations. So in this case, because we are decreasing the volume, the reaction wants to make itself as small as possible. So it is going to shift to the right. That is the side with the fewest number of moles. So again, in both of these cases, A change in volume is going to shift to the left or to the right depending on what the chemical reaction is. So you're going to have to add up your moles on the reactant side and the product side and determine which one has the most number of moles and which one has the fewest number of moles. Now, there are a couple of special cases that I want to address before we move away from changes in pressure. When the number of moles of reactants and products are equal, then a change in volume will not cause the equilibrium to shift. So if we have this equation right here, let's add up our number of moles. We're going to have 1 plus 1, that's 2 on the reactant side, and 1 plus 1, that's 2 on the product side. Again, I'm just adding up my stoichiometric coefficients here. We tend to not write the ones in, but they are still there. So for this reaction, a change in volume, either increasing or decreasing, is not going to shift the equilibrium. Our second special case is when the pressure of the system is increased by adding an inert gas. Again, in that case, there is no shift in the equilibrium. And an inert gas just means it's not going to react with either the reactants or the products. Very commonly, these inert gases are something like neon or argon, basically any of the noble gases, because they tend not to react with anything. So if you add an inert gas, there is no shift in equilibrium. Let's look at one more type of stress that we can apply to a system at equilibrium, and that is changes in temperature or energy. Okay, so we can go back to our generic equation right here, and we need to talk about changes in temperature specific to exothermic and endothermic reactions, starting with exothermic reactions. So if I have an exothermic reaction here, you can think of heat as a product. If you think about heat as a product, then we can apply our rules for changing amounts. So for example, if we decrease the temperature or the energy, we're going to shift the equilibrium to the right or towards the products. So you can think about this as decreasing the amount of one of our products, heat or energy, and we're going to shift towards that decrease. The opposite is also true. If you are going to increase the energy, then you're going to shift the equilibrium to the left or towards the reactants. So you can think of this as adding product, we're going to shift away from it. Now let's talk about endothermic reactions. In an endothermic reaction, you can think of heat as a reactant, which means we can still use our rules for changing amounts. So for an endothermic reaction, if we decrease the energy, we're going to shift the equilibrium to the left or towards the reactants. And of course, we have the opposite. So if we increase the energy, we're going to shift to the right or towards the products. Again, you can think of this as adding a reactant. We're going to shift away from it. So I like to correlate a change in energy with a changing amount of either reactants or products. But of course, it's very important to know whether you're talking about an exothermic or an endothermic reaction. I hope you found this video helpful, and thanks so much for watching.